All right. So we left off right here with this rock in the back of the truck. One word to describe that: inertia. Okay, so what is the second law of motion? When a force acts upon it. So we have to continually look at these laws in relation to each other. That first law said nothing moves unless a force is acted upon it. If it is in motion, it will stay in motion unless a motion or a force is acted upon it. So now here we are. What happens when a force is acted upon it? So this is typically a push or a pull. Finally get some common sense in here. So when a force acts, such as a push or a pull on an object, it's changing the object's speed or direction. In other words, it makes the object accelerate. Remember the definition of accelerate: a change in direction or speed. So anything that speeds up or changes the direction, there's an acceleration there. The reason it changes the acceleration is because a change in direction usually involves a change in speed. Just think of yourself driving. You take the corners at the same speed as you take a straightaway? No, not at all. So you slow down, you change directions, you speed up. So you got many changes in direction and speed or velocity there. So the bigger the force, the more the object then has to accelerate. Take a moment to appreciate this cartoon. So look at this girl here. Here's Newton's second law of motion. The force of the girl accelerates the box. But what other forces are acting upon this box? After yesterday's lecture, you should know that there are two forces not shown in this picture. The box is being dragged along the floor, and that's friction. And something is pulling it down. That friction is dependent on its mass. If it's very heavy, gravity is pulling it down pretty hard, which is going to add to the friction. So those are two things to continue to consider, though they're not a part of this picture. So this girl is going to have to overcome what force? Overcome gravity and friction. So the force of the girl then accelerates the box. The same force would accelerate two boxes only half as much. Or said another way, she would have to use twice the amount of force or work to move two boxes the same distance as she moved the first box. I'm going to have to rewind me and hear that again. Three boxes would only go 1/3 as much acceleration as the first one. So look at these vector arrows here. These vectors indicate not only force but also distance. So look with how much ease the first box goes. We're going to assume she's putting all her might in this one box, and it goes this far. All of her might into two boxes, just like it would go half as far. All of her might into three boxes would go 1/3 as far, because each of those boxes have this equal mass, pretend, and so you have to have that same force in each of those. So mass is the object. The mass of an object affects the inertia. The heavier it is, the more inertia it has. We've experienced this in our own lives, right? The heavier we are, the more inertia we have. The lighter we are, the easier it is for us to move. So objects with more mass have more inertia than an object with a smaller mass. In a marathon, there's me, and if y'all know me, you know my size. I had my small breakfast in the hotel, got to the marathon point, got to my position. I think I had one squeezy carbohydrate juice drink, and that was it. You don't want to put too much in your belly before a big race. And then a friend was about 6'2", which if you don't remember me, I'm only about 5'7". So that puts him about 5, 6, 7 inches taller. And he was a good probably 60 pounds heavier, about 180 to 200 pounds. And right before the marathon, he's still putting bananas in his mouth. He says, well, it doesn't take as much energy for you to move yourself 1 mile. He goes, but I'm a big guy. I need more energy to move this. And why is that? Because he simply has more mass, right? It's going to take more energy to overcome the inertia. So it's harder to make a large object move or change the speed and direction of it when it's moving. That's why we send the kids to get our drinks, right? That's why we send the kids to the fridge. Third law of motion. When a force acts on an object, there's equal force, and that's called a reaction. You might think of a gun, recoil. There's a big boom going in one direction, but you feel the recoil or the reaction coming back against you. That's the kick, right? So when a force acts on an object, there's an equal force acting in the opposite direction. This is a balloon. All the force, work, and energy that you put into blowing up a balloon, right, has been stored up. The moment you let that go, that air is going to push on the balloon. So that's a reaction to the action. The action is the air rushes out. As the air rushes out in one direction, the reaction is the balloon goes up, uncontrollably flying in every direction. So this law is sometimes written that actions are equal and opposite. And here's Newton's balls right here. You might have seen this before. This needs to be animated. So all the momentum, all the force with which this ball hits this one travels through and moves this one up, and it comes back and forth and back and forth. That momentum is traveling. So third law of motion is that there's equal and opposite reaction. When you're pushing hard on a wall, although it's not moving, that wall is also pushing right back with the same strength against you. This is Newton's third law. I push on the door pushes back on me. I pull the door is pulling back on me. This kind of goes along with the first law in that things tend to resist. Things that are still tend to want to stay still. Things in motion tend to stay in motion. The third law pairs up. So my force on the door equals the door's force on me. All right, so this would be Wednesday's lecture. Tomorrow we'll go finish up with types of forces. You've already been introduced to forces Monday, and you saw Tuesday there was gravity and friction as types of forces. Today you saw Newton's 3 laws, the completion of his 3 laws, and now we're ready to go into the types of forces for Thursday. All right, enjoy. Whoops.